Let's look at the next step, stoichiometry, limiting reactants, and excess reactants. Now, the limiting reactants, determining which one that is something that people seem to stumble on quite a bit, but really it's quite a simple thing. I'll try to show you the concepts of what the limiting reactant is here by using s'mores. If you've never had a s'more, now's the time. You need to have a s'more. It's just where you take a graham cracker and a marshmallow and some chocolate and you heat up or roast up that marshmallow and you squish it all together and you get a yummy snack. Now we can turn this into we'll call it our chemical equation, and we can say that in order to make a s'more, this is our recipe, we need 2 graham crackers, 2 graham crackers, plus 1 marshmallow, plus let's say 3 chocolate pieces. Can't use just one. Those are going to react to form one s'more. So now we know what our recipe is, but if we were go to the store and buy supplies, maybe we can't buy supplies in those exact ratios. If we can't, then we're probably going to run out of one of those things before we're done making as many s'mores as we'd like to make. So let's go to the store and pick up some supplies for s'mores. So let's say we've picked up 5 graham crackers and we go to the store and we get 1, 2, 3, 4 marshmallows. And then we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 chocolate pieces. So let's put our chemical equation back up here at the top, or our recipe for s'mores. We said that we're going to use 2 graham crackers plus 1 marshmallow plus 3 chocolate pieces to make one s'more. Now, if these items are what we purchased at the store, we ended up with 5 graham crackers, 4 marshmallows, and 15 chocolate pieces. We should now be able to figure out what the limiting reactant is. If you take a moment, you'd be able to figure this out pretty quickly. Now, just with our graham crackers here, we need 2 to make one s'more. So that would make a s'more if we use those 2, and then we could make another s'more, which means we could make 2 s'mores out of the graham crackers that we have. With the marshmallows we have, we could make 4 s'mores because we only need 1 per s'more. With the chocolate pieces, we could use up those 3. That would make 1. We could use up 3 more. 1, 2, 3. That would make another one. So I'm just tallying them. We could use 1, 2, 3, and that would make another one. 1, 2, 3 would make 1 more, and 1, 2, 3 would make another one. So that would make 5. Now, of course, simple math, you could have figured that out on your own. So with all the supplies that we bought, the maximum amount we could have made was 5. But it looks like because we didn't buy very many graham crackers, we're only going to be able to make 2. Which means, in this whole idea of limiting reactants, the graham crackers are our limiting reactant. That's the one that's going to limit how many s'mores we can make. Now, we can figure out the excess. We're actually going to have 1 graham cracker left over. We're going to have 2 marshmallows left over. And we can also figure out how many chocolate pieces we're going to have left over. That's how we do excess reactant. Now, of course, in chemistry, we have to do a little more work with that, and we oftentimes start with grams. We need to turn it into moles and turn it into grams. But we can do all those things. And I've got some what I call simple steps to get you to that point. The problem is there's just a lot of things to keep track as you go through. But one thing that I always say is it's no more difficult than figuring out s'mores. If you think of these as recipes and you go to the store and you purchase things, all you're trying to do is figure out, well, which one did I not buy enough of? And when I run out of that one, how much of the other stuff am I going to have left over? That's all limiting and excess reactants are. So I'm not going to read everything on these slides, but I would highly encourage you to write them down. And as I've told you before on my lectures and videos, anything that's in a box is super important. When I'm flipping back through my notes, I look for the things in the boxes because that's formulas, that's help, maybe it's equations, things that I need to understand chemistry better. So when you're looking at limiting reactants, these are what I think are the 8 simple steps, and really there's 7, but number 8 is actually the most important because once you can do this, you're one of very few people in the world actually that is capable of figuring out limiting reactants. So it's important to smile and be proud of yourself when you're done. But As you look through these, write them down. I am going to go through this step by step on an example, and this will help you determine the limiting reactant. Now, if you don't watch the example, which is coming up next, this is probably going to be terribly confusing. But if you have this down on your own, you can make extra notes next to it as I'm going along, maybe things that help you understand it a little better. Once you've figured out the limiting reactant, the one that you're going to run out of, in our case, that was the graham crackers, we can then go and figure out, okay, well, I have all this other stuff left over, and I should be able to figure out how much of that other stuff do I have left over. That's called the excess reactant. And here's the 5 simple steps for successful excess reactants in stoichiometry, although of course there's 4, but number 5 is pretty important. And really, once you get to number 5 here, you are almost completely done with all the parts and pieces of stoichiometry. There's one more thing called percent yield, but it involves all of these things in just one more easy step, and I'll cover that one later on. So it's going to get kind of lengthy in the next part, but I'm going to go through a whole example of how to do limiting reactant stoichiometry. So bear with me. Here we go. All right, first one we're going to look at. The reaction between solid white phosphorus and oxygen gas produces solid tetraphosphorus dicoxide. This is a picture of that reaction happening in World War I. They tried to use solid white phosphorus as bombs, mainly to drop over ships. When that bomb canister would open up and be exposed to oxygen, you'd get this reaction to happen. So here's what we did. We went to the store, we'll call it that, and we bought 25 grams of phosphorus and 50 grams of oxygen. We combined those together. The question is asking us how much of the excess reactant remains after the reaction stops. Now we're going to answer all the questions. We got to figure out what is the limiting reactant. We've got to figure out all the parts and pieces, and it'll take us a little while to get all the way to the end to answer that excess reactant. So I've taken that question from the last slide and I've put it on here along with the 8 simple steps and the 5 steps for excess, and I've already got everything written out. Now maybe I should write it out along with you, but it takes a really long time, so you can sort of pause in between and write this out on your own paper. I'm just going to walk you through the steps because most of the stoichiometry are things that we've covered before. Really the big differences here are finding out the limiting reactant and then finding out how much excess there is. So again, I've got the exact same equation up here, or the exact same problem. We're just going to start checking off our list and making sure we have everything. Now I've balanced the equation. We have solid phosphorus plus oxygen gas reacts to form P4O10. I balanced it by putting a 5 there so that the oxygens would match. The phosphorus already do, so I can check that one off my list. And then I convert all known reactants from grams to moles, because in stoichiometry we do everything in moles. You can see I've underlined them in green up here. My knowns are the things that are given to me in the equation. In this case, this is what we went and bought at the store, 25 grams of phosphorus and 50 grams of oxygen. Now we need to convert those known reactants from grams to moles, so I'm going to come right over here. I started with the phosphorus, 25 grams, and I need to have grams on the bottom of my next conversion factor and moles on the top, so I'm turning it into moles. To get this number right here, I figured out the molar mass of P4. So I looked up the mass of phosphorus on my periodic table, times it by 4. This is the number I get. When I do the math on that, that's how many moles of phosphorus I bought at the store. Now for the oxygen, I bought 50 grams of oxygen. It tells me right up here in my known. And O2 is oxygen gas. So I looked up the mass of oxygen, 15.99, times it by 2, I get the mass of oxygen. That's the mass in 1 mole of oxygen gas, and here's what I get. So I have now converted everything to known. I'm going to need those several times, so I'm going to be coming back up to this spot quite a bit as we work our way through here. The next part says write the mole ratio of reactants from balanced chemical equation. This is where people start to get confused, so bear with me. The mole ratio of the reactants, so here's the reactants, there and there. The mole ratio is how many moles are there? There's 1 mole of phosphorus, 5 moles of oxygen. So I've got it in blue right over here. You can do this either way. I could have put the phosphorus on the top or the oxygen on the bottom. But if you look, the whole goal of this step, and we're trying to figure out the limiting reactant, is to get our answer over 1. You'll see why in just a second. Once we have it over 1, we can compare it. So What I did was I chose to put the oxygen on the top because I only have 1 mole of phosphorus if I look right up here. Then I didn't have to do any math with that one. So that basically takes care of this step, right? The mole ratio of reactants from balanced chemical equation. Again, you can put either one on the top and either one on the bottom. You're just going to have to be consistent throughout. And then divide the ratio to get an answer over 1. I don't have to. 5 divided by 1 is 5 over 1. So I can leave everything just the way I've got it right here. Step 4. Write the mole ratio of reactants from the known mole ratios. Now let me remind you, the known, I'm going to scroll up. The known is the stuff that we purchased at the store. And we've already turned those into moles over here in green. Now I don't have this one on here, but I'm going to put it up here real quick. All I need to do for this part is keep them in the same order. So I have to have oxygen on the top. So if I was to take my oxygen, I've got moles of oxygen, and then I need to put that over moles of phosphorus, just like I did in blue right below here. Okay, and I need a division line. And then if I get out my trusty calculator and take 1.56 divided by 2.02, I'm going to end up with 7.72. I take my 7.72 and I put it over 1 because anything over 1 is the same. And I didn't have anything to cancel my units, so they stay the same. Notice how this in red is just a simplified form of this in green. And the reason is we need to get this over 1. If you look, we're comparing. We've got 1 mole of solid phosphorus on the bottom of both of these. Now we can use this to figure out our limiting and our excess reactant. So here's where people get confused. Bear with me. In blue, right here, well, let me check some things off. We've now done number 4 because we divided and we got this. So we're working with the red one. This one's going to go away. I'm going to move it away in just a second. Now number 5 says determine the limiting reactant by comparing both ratios. So let's compare them. In blue, this is from our recipe right up here. So this is what the recipe calls for. We should have 5 moles of oxygen for every 1 mole of solid phosphorus. Now the stuff in green that we worked with right here, this is what we bought at the store. Let me scroll up. This is just this ratio after we've done some work with it. So that's what we bought at the store. Then we simplified it over 1. Now look, the recipe calls for 5 moles of oxygen gas for every 1 mole of phosphorus. When we went to the store, we purchased 7.72 moles of oxygen gas for every 1 mole of phosphorus. That looks like to me we bought too much oxygen gas. So we're not going to run out of oxygen gas when we do this. We're going to have oxygen gas left over, which is why we can come over here now and say, well, we didn't actually figure out our limiting reactant. We actually figured out our excess reactant, which is oxygen gas. But if I go to my balanced chemical equation, because there are only 2 reactants here, if this one's in excess, we're going to have some left over, then that obviously means that we're going to run out of phosphorus at some point. That's the one that's going to determine how much of this product we can actually create. So let me come down here in my fancy bubble. Now we know then that the limiting reactant is the solid phosphorus P4. I've got another example after this one in a different video, so if you need more work with figuring out this limiting reactant, the problem is people start to overthink it. They get tricky, and don't overthink it. Okay? So now we know our excess and we know our limiting. And because we know our excess and limiting, we can check off number 5. We have determined the limiting reactant. Now, remember, we're trying to figure out how much of the excess reactant remains after the reaction stops. We could go right to that point right now, but I'm going to work my way all the way through here. Now here's the great thing if you use the steps. Any question that you can be asked is going to come out in these steps. So you just need to, if you work your way all the way through, you're going to figure out, well, what is the limiting reactant? What is the excess reactant? How much am I going to be able to create? How much product? How much excess is going to be left over? Any question that can be thrown at you is going to be answered throughout these steps. Okay? So I'm going to go to step 6. Calculate the moles of product from the limiting reactant. Moles of product. Okay, let's go back up here. Moles of product is how much is what I'm trying to solve for. Okay, product right here. So these were our reactants. This is our product, P4O10. All right? This says calculate moles of product. I need to calculate how many moles of this, and I need to start with the limiting reactant. I come back down here, my limiting reactant was P4. Now, bear with me. I bought 25 grams of phosphorus at the store, but I always do everything in moles in stoichiometry. And I've already turned this into moles right here. I did the work for myself. So I need to start with 0.202 moles of P4 and turn that into moles of product. If you come down here, that's what I've done. The 0.202 moles of phosphorus, I need to have moles of phosphorus on the bottom, so that cancels out. I'm trying to turn moles of phosphorus into moles of P4O10. And where did I get these numbers? Anytime I have mole and mole, a mole ratio, I go up to my balanced chemical equation and figure out what they need to be. So I need to look at P4O10 and P4. So here's P4, there's an imaginary one there. P4O10, there's an imaginary one right there. That's where these ones came from. That's going to cancel. I come over here, I'm left with 0.202 moles of P4O10. So, I've just finished this part. I figured out how many moles of limiting reactant, or how many moles of product from the limiting reactant. We have to use the limiting reactant because that's the one that's going to determine how much we can make. That's the one we're going to run out of. The next step here, calculate the mass of product from the moles of product. So let me scroll down here. Now moles of product is what we figured out right here. This is how many moles we're going to be able to produce. But moles doesn't do us a whole lot of good. It's what we use for the stoichiometry and to do the math, but we need to know grams. So I start with the moles of product, and I need to turn that into grams of product. So if you look at my work here, right here I have to have moles on the bottom so that this will cancel out, and I need to turn that into grams, so I have grams at the top. Now where did I get this number? 283.78. Well, if I have moles and mass, I need the molar mass. So down here in red, I had to figure out, okay, I've got 4 phosphorus. This is the mass of 1 phosphorus. I have to times it by 4 because I have 4 of them. Here's what I get. Same for oxygen. I've got 10 of them with this mass. Of course, these mass are a little bit rounded off, but this works. And then I add those two together. That's where I get this number. That's the molar mass of P4O10. I plug it up here. Those two cancel out. 2.02 times 283.78, and I get 57.32 grams of P4O10. That's how much I'm going to produce when let me scroll up, when I go to the store and buy 25 grams of phosphorus and 50 grams of oxygen. This is hugely important in a lab. So you need to figure out, well, how much product am I going to be able to produce if I order this much material? Or I need to produce this much stuff. How much do I need to order? Now, we've done essentially everything we need for limiting reactant stoichiometry. We've figured out the product. However, how much of the excess reactant remains after the reaction stops? We haven't done that. That's important as well because you need to know, well, if I run this reaction and I have stuff left over, how much do I have left over? And then I don't need to order that much stuff next time. So let's go down here. We're going to be using our end product number, and I've set up the 5 simple steps. Get rid of those so we can work our way through them. And number 1, first perform all the steps for limiting reactant stoichiometry. Well, this is easy. We did all that. So we're done with number 1. Number 2 says calculate the moles of excess reactant from starting moles of limiting reactant. So let's tear this apart. Calculate the moles of excess reactant from the starting moles of limiting reactant. Okay? The excess, let me scroll up. The excess reactant is right up here. Oxygen gas, our limiting was phosphorus. So that's what we've done right here. I've taken right here the starting moles of limiting reactant, 0.202 moles of phosphorus, and I'm trying to turn that into moles of excess. So right over here, moles of our excess. To convert that, I have to put moles of phosphorus on the bottom so it cancels out, and moles of oxygen on the top. This is a molar ratio. Now where do I get the number for mole ratios? back in my balanced chemical equation, which is why this is in blue. So I'm going to scroll up here to the top. Here's our balanced chemical equation. So that's where we got the numbers for our, there's the 5 right here. Let me come back down. So when we do the math on this, we get 1.01 moles of excess reactant. So 1.01 moles of oxygen gas. The next part says, let me get rid of this, convert the moles of excess reactant, that's what we just started, or we just answered for here, convert the moles of excess reactant to grams. This is how much is needed for the reaction to fully occur. So convert moles of excess reactant to gram. We have the moles of excess reactant right here. I've just moved it over here because I ran out of room. And I need to convert that into grams of excess reactant. So that's what I'm ending with over here. So I've got 1.01 moles of oxygen gas. Have to put moles of oxygen on the bottom and grams of oxygen on the top. And where did I get this number? Well, that's the mass of oxygen gas. 15.99, which is 1 oxygen, times 2 gives me that number. I do the math and I end up right here. 32.3 grams of oxygen. Now why do I have a blue line around this, or a blue circle around this? This is what is needed for the reaction to fully occur. So we have our needed right here, 32.3 grams. That is how much is going to be used up in the reaction, because we're going to be running out of phosphorus and we're going to have some of our oxygen left over. But this is how much is going to be used when we use up all of our phosphorus. The available part is the known excess reactant amount from the question. In other words, this is what we went and bought at the store. So the available is what we purchased at the store. Let's go way back up here to the top. That says right here, we purchased 50 grams of oxygen at the store. So let's go put that back down here. We've got our 50 grams of oxygen minus our 32 grams of oxygen, which is how much is going to be used up. When we do the simple math, we subtract those two, we end up with 17.7 grams of oxygen. And what that means is we'll have 17.7 grams of oxygen left over when we're done, and now we can breathe, and of course we can finally smile. So these limiting reactant, excess reactants, they just take a lot of work. If you keep yourself organized, keep all your parts and pieces together, you're going to get there. Just keep pushing your way through. Again, once you have this stuff down, boy, I am confident you can do just about anything in chemistry, especially in a lab situation. Now, I've got another example. That'll be in the next video. Didn't want to attach it to this one to make this one overly long. So if you need help with one more, go find the next video. And then we're going to look at percent yield, and then you got stoichiometry all figured out. So good luck.